from the scratch until the end, just to end out by a good geomechanical model. So the first step is to build overburden gradient. As you know, overburden gradient, in other words, vertical stress and or lithostatic stress. It mainly comes from the weight of the rock above a certain point, and we are normally using the density log from the offset wells. By the way, it's a very tricky step. Overburden calculation. It's a little bit tricky, especially in the deviated wells. You can imagine that the vertical section, especially in the deviated well, have a different variation, especially if you are dealing with severe water depth variation, or even if you decided to drill an offshore well from the land, or from using onshore rig itself. So there is one of the uncertainties in your model. Another case that we have lacking the density data, which is common in most of our field, especially in the late life of the field, you will suffer from lack of data, of density data itself. So it will add another uncertainty while you are building the overburden gradient. It may result, and you can imagine, it may result for a difference range to 3 ppg difference between the upper case and the lower case. This 3 ppg may impact significantly on the fracture pressure and the safe mode window you need to identify for the drilling guys. And by the way, all of these clues and the tricks will be discussed in our upcoming course, inshallah, and we will talk. We will not have, we don't have right now the window to talk about all of these tricks, all of this message you have to be familiar with. That's why we will go in deep through our course, inshallah. The second step is to identify the pore pressure. Pore pressure calculation step, it's very essential and vital one. So I want to just focus on this one, and I will give you another slide just to focus on the different methods using to identify or to calculate the pore pressure. So there are many different methods used to calculate the pore pressure. The most significant and the common ones are Eaton, Bowers, and Trowit. If we just have a highlight for Eaton equation, which is the most common one, you just have a look about this equation or these figures. For the Eaton method, they use different logs, including resistivity, sonic, density, and even the D exponent itself. So all of these logs have been used to identify the same idea. There is normal convection trend, which is this straight line, okay? And any deflection from this straight line will be considered as an overpressure zone. What does it mean? It means that you are considering that you have a continuous and uniform convection trend from the surface until the TD of the section itself, and based on the convection trend of the shales itself, you will assign to draw a normal convection trend, showing for you that you have a consistent convection trend. That's why if you find out any deflection at this logs, it means that at this interval you have lower density than the assumed due to the abnormal convection trend. This means at this level that you have a higher porosity than the assumed at this level of the convection trend. Also for the sonic, the same issue. You have found slower formation related to the normal convection trend, and also the resistivity curve. So in consequences, if you calculated using the Eaton equation, you would find that this section is overpressured due to the deflection from the normal convection trend. Identifying normal convection trend is not such easy step, and as you know, it's the most critical factor while calculating it. The main question here, will you use only one normal convection trend or more? Do you assume that you have a continuous deposition without any changing in the depositional rate or not? It's very critical for you. Your experience in the field, the 1D basin modeling you have to build, all of this data will help you just to to be familiar more with your trends. Either you will use one normal convection trend or more. And by the way, again, we will dig in deeply in the course with such tricks for building normal convection trend. And using any methods will have the same uncertainty. Again, using validation data for the pressure, including MDT, RFT, or even DST, will always be the ideal solution and a good validation for you.